Fernando Ventura, speaking about unsupervised learning approaches to classifying extended radio sources with MeerKAT.
Good morning. Today I would like to present a unsupervised learning approach to finding exotic radio galaxies in MeerKAT MGCLS data. So, first of all, why do we want to do this? Well, as you know, modern and future surveys produce a lot of data. New instruments such as MeerKAT and the SKA produce massive surveys that have tens of thousands, if not hundreds of thousands of sources, and extracting what we want out of that manually is tedious and unfeasible. So, the data we're using from MeerKAT, from the MGCLS survey, so legacy cluster survey in the radio spectrum, and here are, so just briefly what we're looking for. So we are looking for radio galaxies, and we're not looking for the more normal FR1 or FR2 type galaxies. So of course, Fernando Ventura class 1 and 2. Then there are more interesting ones such as bent-tailed and egg-shaped, and we want to find the more exotic things here. So, and of course there's some cluster emission that also comes up a lot in these images. So we are looking for the more unusual sources. So an autoencoder, briefly, is an unsupervised learning approach where we have two neural networks, one of which takes input and tries to map it onto some latent space as an encoded form, and then the decoder is some form that takes the encoded form and tries to map it back into the original image. So training can be done unsupervised because we can compare the input image to the reconstructed image, and then it can compare that without human intervention and backpropagate the errors through the neural networks. Spatial pooling layers are a layer for a neural network that will remove the influence of sizes of the images. We want this because, again, the apparent size of a galaxy in a survey is not going to be relevant to its morphological classification, because it could be any distance or due to the, the size of it. So that shouldn't really affect classification, and pyramidal pooling layers remove the influence. So they are a feature reduction layer. They reduce down our data. So here's basically what it looks like. So you have an autoencoder, takes the input image through a pooling layer, regular convolutional layers, encoded form, decoder, tries to reverse that. So we will train the autoencoders on the more usual images, like FR1s and FR2s. So hopefully it will learn to reconstruct these really well, which means that when it gets something more exotic, it will struggle to reconstruct it, and we can then use that to detect these unusual images. Finally, ensembles. So ensembles are where we basically tie the autoencoders together. We use the variations between multiple autoencoders, in our case 3, with different latent spaces. So the restrictions we place on the encoded form will determine how they behave, and then this can produce better results. So how did we prepare our data? Well, first we take the MeerKAT images, then we use a software called PyBDSF to extract or find the relevant sources. PyBDSF will tell us which sources are point sources or Gaussian blobs. We don't want those, so we remove them. And then we take the selected images, run them through another rough filter trying to extract sort of point source type things because we don't want those. We then take cutouts. We manually label these for our training and testing purposes. And then because manually labeling didn't produce obviously a lot of images, we augmented the images by rotation because, again, flipping and rotation, that should not affect the classification because the galaxy can obviously be oriented in any way on the sky. And this produced about 3,000 images for training, so this is quite a small data set, and I should mention that already. So here we have the results from a single convolutional, from a single autoencoder. Now these are the so in each, at the top we have the training, the best reconstructed training data. In the middle, the best reconstructed typical data, which is what we're not looking for, which it should reconstruct well. And at the bottom, the best reconstructed exotic images. So the bottom 2 rows are testing, and in each big row, the row on top shows the original, and the row below shows the reconstruction. So you can see here already that FR2s, it does tend to do very well, and the exotics, which it is reconstructing well. So these are the ones it will have the most difficulty finding, do tend to be exotics that have a more traditional sort of lobe structure. Now, these are the ones it has the worst reconstruction of. So as you can see, it struggles with contrast, so really low contrast images, it struggles to reconstruct. But notice the exotics at the bottom. See that the ones that it most struggles to reconstruct are the ones that look the most different from sort of FR1, FR2 type structures, your sort of galaxy remnants, that sort of thing. And so it means that finding these is the easiest. These are the easiest things to extract from it. Even so, here is the distribution of the reconstruction. So we use the normalized cross correlation as a measure of reconstruction. And as you can see, the distributions of the exotics skews more to the low end, as we would expect. However, both peak quite high, which means that separating the two is not that good. And as you can see, it does have some effect, but the F1 score is still, which is a measure of the recall and precision together, is not too high. However, let us now look at what happens when we use an ensemble. So we have here 3 autoencoders that have their output combined in 2 different ways. On the left, we have the average reconstruction error tested against the threshold. But on the right, we test each reconstruction error against the threshold individually and then allow them to basically vote on the classification. And as you can see, that gives us a massive performance improvement because you can see the classification here is way better. And obviously, we cannot just pick the best threshold. So the threshold would be determined through testing because you would not know the best threshold for your data. If you did, there would be no point in this. But we can get an F1 score above 0.9, and that's actually, this is a massive improvement over the previous generation. But I should mention again that this is quite a small data set, and this is a new avenue we're exploring, and although it shows a lot of promise, more testing definitely required. So, yes, if we look at the receiver operating characteristic and the confusion matrix for it, we notice that actually they have, it's performing very well. And definitely this is the avenue we'll be exploring going forward, is looking at the ensemble using a voting type mechanism to determine which are exotics. And of course, I should say that here our categories are quite broad. So we've been trying to separate typical sources from exotic sources, but that's very broad. So if we train this on something more specific, like if you were trying to say find only egg-shaped sources and you trained it on everything that's not an egg-shaped, you could have a more accurate performance. So the way this would be used is it would be imperfect, but it would present you with a lot of candidates for what you want. And you will use it doesn't go back. Sorry. So you will use the candidates that you would then manually search. So it would not be you would not just take it at its word, but if you are looking for something specific, you can use it to find the best candidates for whatever it is that you're looking for. And it's very fast. So running this once it's trained, running this on tens or hundreds of thousands of images is relatively quick, and we can definitely much more easily find the candidates of whatever study you're trying to do. You can process in a day, you can get enough candidates for your study, when previously you would have to manually spend weeks perhaps manually classifying these to find your ideal data. So going forward, this is the approach we'll be exploring, and I hope you can agree that it shows a lot of promise in finding exotic sources in radio galaxy data. Thank you.
Thank you, Fernando. We have a few questions on the live question channel. Some of them are from people in the room. If you'd like to ask the question directly. Please go ahead. Please come to the microphone at the front of the room.
Oh yeah, so you spoke about how you use PyBDSF to first remove all the compact emission. So what happens in the case where like the compact emission is part of the exotic structure that you are trying to classify?
What happens when it's, so you mean if it's part of the source? Yeah, so how PyBDSF works is it finds the bright points in your image, and then it finds an island around that image. So it will find the bright point, and then it will include as part of the source anything around it that has above a certain contrast ratio. So if the source was, if it's part of the source, it's typically connected by some diffuse emission, and that emission should then be above the threshold, and it would return that as a single source. What we were removing there were things that were unconnected. So if it tells us, here's a bright thing, and maybe there's some emission around it, but it's just a blob and nothing connected. And it is also not perfect, so.
Thank you. Michelle Lochner, are you in the room?
Cool. Thanks. Thanks for the great talk, Fernando. It's basically a follow-up question. I didn't really follow, because we know PyBDSF kind of sucks at source finding, especially for the extended sources. No offense to everyone who loves PyBDSF, we all love it, but the source finding step is often the hardest, and there's often a lot of manual work that has to go into actually identifying this is one single source. Like often you'll have several, it'll see the same source as several different sources. So I just missed a little bit. Like I get throwing away all the compact sources, fine, but how did you actually build a curated training set? And there's also the issue of sources being on very different scales, for instance. Yeah. So I'm kind of interested in that step and how much manual work that took.
Okay, so after we took PyBDSF, it does still return, so we put it on almost a mode of rather return more sources than fewer. Yeah. So a lot of point sources and blobs were still included in that, even after that step. And as I say, it is imperfect, so we weren't trying to create a definitive catalog of every source in this image, just enough for our testing purposes. But after that, ran a rough filter, sort of trying to fit a Gaussian to it, and if it was successful enough, throw it away as well. And then it is manual. And in the manual process, so to create our set for testing, that was very manual, and so as I say here, the manually labeled images, to create the labeled images, that was a manual process. And what we had was, we had like an interface, and you could select different categories for the interface. And there were certain buttons for PyBDSF has messed this thing up, throw it away, or this should not be included, or PyBDSF got something wrong, reprocess this image. So yeah, you're right, it does have a lot of errors, but it was just a way to basically cut down the work before we went to the manual labeling. So
yeah, that's completely understandable, and I'm in the same boat with my stuff. But I think it's a step that we have to fix if we want to really automate these methods and find good ways of doing it. Definitely.
Yeah. So I mentioned we had about 3,000. So the testing and the training sources together were about 3,500 or 4,000 images. But what PyBDSF had returned to us was like 5.5. So of that 5.5, after we had gone through them, only like 3.5 were actually used. But that's still, okay, yes, you have to go to 5,500 images, but then that's not 100,000 images. So, yeah.
Sure. Cool. Can I ask another question? Or do you have other questions on Slack?
Short one.
Okay. Just very quickly, did you have a look at the latent space and see if you could gain a bit of intuition about
Yeah.
what it's trying to learn from the galaxies?
So I have an extra slide just in case someone
well
asks this.
prepared.
And I accidentally went to it, but yeah. So this is the latent space. So they are quite high dimensional, as you can see. Yeah, they are quite high dimensional, but we use PCA, which is just a way of projecting data down. And as you can see, there's some separation. The exotics are in red, but nothing really. However, they were not really set up to separate things necessarily. So, yeah, we did look at the latent space, but we were not necessarily expecting anything there, and we didn't find anything there, but we did have a look at them in PCA just to see in case it did something. But, yeah.
Okay, cool. Thanks so much.
So we have two more questions on the channel.
Okay.
First one from Simone Riggi. What did you do to handle the background sources, e.g. the point-like sources? Did you detect them with PyBDSF and then mask them or replace with background? Or do you only compute the loss on galaxy pixels or both?
So we actually tried a couple of approaches. We did try to mask them out with PyBDSF detections, but it didn't work very well. And then in the end, what we did is we just took a very close cutout of the source so that, any nearby but not quite background sources were excluded. And then anything that was too obscured by background sources, we did not use for this. But mostly the source that it was passed into the machine was just a close cutout of the source itself as it is found with no additional masking. Although we did try various approaches for that, and then eventually we just decided this was the best way to do it.
Thank you. And one final question from Dirk Petrie. How exactly do you determine whether the autoencoder is struggling to reconstruct?
Sorry?
How exactly do you determine whether the autoencoder is struggling to reconstruct?
So after the reconstruction, we take the reconstructed image and the initial image and calculate the normalized cross-correlation, and then we apply some threshold value to that. So if it's too, so it's like a reconstruction error. It's just based on the physical image. So if it's too high, if the reconstruction is good enough, then we assume it's something that it was taught to reconstruct, so a typical image. And if it's poorer, then we assume it's something exotic.
Okay. And there was one final question came in. Do all the cutouts have the same size, and how did you choose this size?
Okay, so as I mentioned earlier, we have the pyramid spatial pooling layer, which will take any apparent size, and it's meant to be a pooling layer that is invariant to the size and will reduce the effect of the size on the classification. So when we had our cutouts, they were all different sizes because, obviously in the image, they're all different sizes in the galaxies or in the cluster image. So the number of pixels eventually that gets passed in is the same. It's just a high number that's high enough to accommodate the various resolutions, but obviously some of them are still low resolution, but the pyramidal spatial pooling layer is meant to take care of that, to allow us some invariance in the size, or the resolution rather, for the encoder purposes, to make sure that's not what it's classifying on.
Okay, thank you very much, Fernando. Thanks again.
Thank you.